This is our presentation on drag and area investigating terminal velocity. An object falling has to displace particles in the medium that it's going through. Drag is the resistance a fluid such as air exerts on an object moving through it. The force of gravity is the attractive force between any two objects with mass, and the terminal velocity is the maximum speed an object can reach while falling through air, at which the force of gravity and drag prevent it from further accelerating. For this project, we wanted to investigate how surface area affects how the magnitude of terminal velocity changes, and this is important because it helps to determine the drag force on the object. This ties into our personal lives because objects falling is part of everyday life, and understanding how different variables affect terminal velocity can improve everyday tools, such as creating safer vehicles, improving sports equipment, or developing new technologies. The research question for our project was, how does different surface areas affect the terminal velocity when dropping a paper plate from the same height? Our goal was to use Tracker to find at which point the paper plate reaches terminal velocity and how that differs among the 3 different plate sizes. We hypothesized that using a bigger plate, even if the mass is kept the same, will result in a slower terminal velocity. This means that the drag force is greater. We think this because having a large surface area means that more particles from the medium are being impacted. If you rearrange the force of drag equation and only focus on terminal velocity and surface area, you get area equals 1 over u squared. For our experiment, we used a meter stick against the wall, small, medium, and large diameter paper plates that were all the same mass, and each size plate was dropped from 1 meter, and the terminal velocity was determined using Tracker software. The controlled variables included mass, drop height, environment, and way of release.
Now I'll talk about our free body diagrams. We have 4 of them here at different points in the fall. First being right after release and the last being after terminal velocity. Right at release, resistive force is very minimal. Force of gravity is the same. And as we increase, the resistive force goes up. And once it reaches terminal velocity, resistive force is equal to force of gravity, and it stays the same from there on. The different plates will have very similar free body diagrams, but there'll be different magnitudes for the forces. Moving on to our system schema and energy pie charts. Our schema has the plate, air, and earth. Earth plays a gravitational role on both of them, negligible for air. And then the paper plate is in contact with both of them, so it's hitting the air as it falls down, and then it hits the earth when it reaches the ground. And then we have our pie charts here, where immediately after release we have high potential energy and very minimal kinetic energy in other forms. And potential energy consistently decreases as we go through, and then kinetic energy increases until we reach terminal velocity, where it stays the same, and then our other forms of energy continue to increase.
This is showing the position versus time graph for the big plate. In order to find terminal velocity on the graph, you see where it is constant and find the slope between those points. The circle captures the terminal velocity point. For the big plate, the terminal velocity is negative 2.32 with an uncertainty of plus or minus 0.60 meters per second. This is showing the same graph for the medium plate, which shows a terminal velocity of negative 2.38 plus or minus 0.62 meters per second. This last graph is showing the small plate terminal velocity, and it has the highest velocity with negative 2.95 plus or minus 0.57 meters per second. The slide shows the calculations of the surface area and the drag coefficient. For the surface area calculation, we needed the mass of the plate and the radius. As you can see on the left, it shows the surface area for each plate size. On the right, it shows the drag coefficient. When hitting terminal velocity, force of drag is equal to force of gravity. For the small plate calculation, we used the surface area, terminal velocity, density of air, which is 1.225 kilograms over meters cubed, and found force of drag through finding the force of gravity. This came out to a number of 1.82. This table summarizes our findings, showing the surface area, terminal velocity, uncertainty, and drag coefficient. And as you can see, as you increase the surface area, the terminal velocity decreases, as well as the drag coefficient.
So now I'll talk about our error and uncertainty. There's a couple places we could have had error, one being the meter stick being misaligned. We try to fix this by taping it to the wall, and the other being movement of the plate in the X directions. And to resolve this, we repeated trials, picked the best one where the fall was most vertical. We also calculated uncertainty for drag using the equation here. And then we have our work to the right here in this picture, where we calculated the uncertainty for area and all the factors, combined it, and have our final uncertainty below. And then moving on to limitations and future directions, we felt like the plate of tumbling and not falling perfectly straight was a pretty big issue. So in the future, we would like to increase the mass to help prevent that. And also maybe do more than 3 different surface area plates, maybe 4 or 5, and just give us a better idea of the pattern.
For our scientific reasoning, we rearrange the drag equation in relation to surface area to see the comparison with the other variables, more specifically the terminal velocity. When increasing surface area, the force of drag increases while the coefficient of drag and terminal velocity decreases. As you saw earlier, the terminal velocity goes from negative 2.95 to negative 2.32, and the coefficient of drag goes from 1.82 to 0.98.